Right, so let's go ahead and get started. What I asked you all to do today was take a first crack at the assignment and begin working out what supplementary document collection do you wish to examine and what progress have you had so far with our algorithms. So I'll just go around, ask each of you to verbally describe where you're at, and I will want you to talk a little bit about why did you find that particular document collection to be of interest? You know, what really made it grab your attention? So Spencer, why don't we start with you?
Okay, so as for like my progress on the assignment so far, I haven't made it that far.
Mhm.
I'm rewatching the lecture trying to like fully grasp.
Yeah.
And I have found my secondary set of documents. It's an IMDb database because
Okay.
I'm a film major as well. So I'm kind of curious to see how like the technical aspects, like technical wordings in film reviews would relate to like this positive negative aspect.
How many samples are in it?
Like I think 2,500
Okay.
or 25,000. It's 25 something.
Yeah. So it's certainly a different data set than the one I included from IMDb, which only has 1,000 samples. And I think you'll have a lot of fun analyzing that and comparing and contrasting sort of where they're coming from. Cool. Dan.
I've made little or no progress on the assignment because I'm fairly confused about exactly what we're supposed to be doing.
Fair enough.
I have some questions I figure I need to get with you on.
Yeah.
And I've looked over it, but I've still got questions.
Yeah.
In terms of the data set, I found a website, Figure 8, that has lots of different scored data sets.
Mhm.
The one I'm looking at right now is New England Patriots Deflategate tweets.
I'm sorry, what?
New England Patriots Deflategate around the 2015 Super Bowl. There was the Deflategate controversy on whether or not they were deflating footballs, whether that was cheating. I just kind of went through the list and it's like, well, that looks interesting. And it was different tweets. There's about 12,000 of them where they have the tweet and they have categorized it as like negative, positive, slightly negative, slightly positive, things like that.
Cool. Eric.
So I got both of the things working. I don't know if they're working perfectly, but
Yeah.
they give a result that is greater than 50% prediction. So
Yeah.
it's not nothing.
Yeah.
I also found a data set on this one website, the Machine Learning Repository that we learned about in scientific computing. And I thought it was interesting because it had like a truly ridiculous amount of documents inside of it. Like just one of the classes is PubMed abstracts, which is 730 million documents.
Sweet.
And there are 6 different types. So of course, I downloaded the 6 gigabytes of file that they have and
Nice.
drastically cut down each one of them into much smaller things. So I have like 3,000 or 4,000 documents in the final thing. And I actually, I just got it running like the test on it. I was able to get like 60% prediction.
Nice.
5 different classifications.
Nice. So what were the classifications?
So there's emails that they got from Enron. There's entire papers from some journal that I've never heard of. There's blog entries, New York Times articles, and abstracts from PubMed articles.
And so these are positive and negative sentiment, or are they labeled in a different way?
In this case, I just like split them up into which of the 5 categories.
Oh, okay. So recognizing a journal article versus a blog and so forth. So that's a really interesting problem to tackle because it's not clear from the get-go how distinct those categories actually are, right? We can have an intuition that the way people do their word selection and the like would be different in a blog than a journal article. And so something like this provides a way of trying to quantify that intuition. So let me give an interesting example of this. I have an old friend from graduate school who's now a professor at the University of Utah. And he made a really, really big splash in the research community about 12 years ago in the following way. He was working on embedded systems with his research group. and they found that they were going crazy because the compilers for some of these platforms were buggy. So in their frustration, they developed an automatic compiler bug detection tool. And the way it worked is to grab multiple compilers, feed a randomly generated C program into it, and see if the outputs of the program were the same for all the compilers. And so they would consider to be correct the output it would give by a majority voting of the 5 or 6 compilers they were using. So what got interesting about this, thinking about blogs versus journal articles, is that he wound up blogging extensively about this. I have to emphasize this was highly successful. His group wound up reporting hundreds of bugs that were fixed in the 2 most important open source C compilers, LLVM and GCC. So this was good stuff. He found that he fundamentally got more of an audience by blogging about his research than publishing about it. So he certainly wrote papers and published about it, largely because being an academic, that's what you do for professional credibility. But in terms of getting impact and getting people to know about his research, he found that blogging got him there in a much stronger way. Where I think this is really fascinating is to ponder, if you examine the way an academic writes a blog post versus a journal article, how different are they going to be? It may be the case that part of the appeal of the blog is there's a tendency to write in a more informal style that's just kind of easier to grasp. That makes this kind of stuff really, really interesting to think about. Cool. I like it. That's a great example. So Innocent, talk about the document collection you've selected and your progress so far in the algorithms.
So I selected reviews for Airbnb. Yeah, in one of the states in US.
Yeah.
It's Massachusetts. So my intent for them, it provide 4 different columns. One of which is like an ID of the person who hosted the person. Like the reviews of the people who got hosted, and I want to classify them in terms of, does this person give better services, or good service, depending on what people that the person hosted said about it.
Right. So that's a really strong sentiment problem. Yeah, that's a really cool idea. Yeah, I like it.
So regarding my progress, I'm still working on Bayesian, naive Bayesian classifier. I feel like I'm sort of halfway done, but I'll see how much I can do for the end of the day. I haven't done much progress on it yet.
All right, Austin.
I chose a data set that does tweets from the U.S. airline, like it does determining whether it was a positive, neutral, or negative experience based on the tweet.
Right.
And so far on naive Bayes, I feel like I'm on the right track, but I'm not finished. But I think I've set it up correctly. I think there may be just few components I need to work out. So
Sure. How big is the volume of this data set?
let's see. Well, it's where do I find that? I think it was like 30,000 or something.
Nice. Yeah, that'll be a lot of fun. That's a cool set. All right, Brandon.
So for progress, I haven't really made any, because I'm so confused on that. But my data set I have is a collection of Steam reviews for video games.
Okay.
I think it's 12,000.
Nice. Yep, sounds good. Jake.
I've made a little bit of progress on notification. And then for my data set, instead of using IMDb, I used apparently Cornell has a movie review area, and that one, their data set has 27,886. To be exact.
Seems a very exceedingly precise outcome. Cool. What intrigued you about that particular database?
I was just looking for sentiment databases. IMDb came up a lot, so I was like, oh, let's try and find something else.
All right.
And I found Cornell, and I didn't know they did movie reviews.
Cool. Very cool. Okay, Caleb.
Well, I guess I'm in a similar situation as a lot of. I've gotten to the point where I know what I need to figure out. I don't know how to figure it out. So I've made enough progress to know where I don't know.
Okay.
But for my database, I chose a Stanford processed set of Rotten Tomato reviews. So I've got 10,605 to go through. And I wanted to do this one specifically because I wanted to see how well it, I guess, maps sarcasm. Because what I found with Rotten Tomatoes is a lot of their reviewers are very sarcastic. So I want to see how well it can read the sarcasm.
Cool. And so, yeah, the first data set I gave you all will then provide an interesting baseline given maybe you haven't quantified it, but you've got the subjective notion that the sarcasm quotient is going to be much higher in that database. Using these kinds of algorithms can be a way to start quantifying some of those hunches or intuitions, which in turn can give us a broader sense of insight about what we're doing. Nice choice. I like it. Mitchell.
So for the night Bayesian, I think I've got maybe about halfway done getting 50% correct and then 0% positive and 100% negative. So I'm not sure what happened. And then for my data set, I got it's a data set of 160,000 tweets with emojis removed. I thought it was interesting because people on Twitter will talk like they can read something negative, but then they can type it in emojis.
Right.
And I wanted to see how it was how I would learn from the machine.
Cool. David.
So I think I might have both of them.
Yeah.
And then also I think two data sets. They're similar in type. One is a subreddit classification. So based off of what a user posts, it's associated with a certain subreddit. And then so those have I think like 15 subreddit. Like
Yes.
too many subs. And then each class within those, and then you classify a new incoming post to the subreddit. And then same with YouTube metadata. Based off of the title of the video or the actual description of the video, you classify which category that YouTube classifies it as. So does it go into like sports or home life or something like that?
Cool. All right. Will.
I've made no progress because one, I'm a little bit confused about all the naive plays, and two, all my files are showing up as read only for some reason.
Nice. Nice. Yeah. What about data set?
That's one I'm still considering.
Have you looked at some options?
Yeah,
So what are some options you've considered?
probably using an IMDb reviews of good movies and bad movies.
So how is good and bad defined?
I'm more looking at for ones that like are more bad movies that everyone just loves for some reason. And the good one, I'm still figuring that one out.
Okay. Cool. Cam.
I haven't made a full lot of progress in the budget, but for my data set, coincidentally, I think I might have chosen the same data set that he chose for the Rotten Tomatoes.
Okay.
That has 2,605.
Yeah, the overly precise number gives a hint that it's the same one. Cool. All right, so something that I think is, kind of fun and exciting about what we've been discussing here is that we should have a pretty good variety of different kinds of data sets to have a conversation about on Tuesday when you all present your results, you know? And so something that's kind of in the spirit of this assignment is to say, it's really hard to talk about whether something's a good classifier or a bad classifier without some kind of benchmark, without some kind of baseline way of saying, here's something to compare it to. When we talk about whether a machine learning algorithm is performing well, then there is the notion that the further from 50% you are, certainly the better it is. And the reason I say further from 50% is that let's say you've got a machine learning algorithm that is 5% accurate. I'm going to suggest it's awesome. Why might I say that?
Always just invert prediction.
Yeah, exactly, right? See, if you've got 5% accuracy, which looks horrible, it could just reflect that it has somehow learned the inverse of what you want. And so then you can just invert its prediction and suddenly have a 95% classifier. So distance from 50% says a lot about how good it is. That said, we can't talk about it in an absolute sense. And the reason we can't talk about it in an absolute sense is the fact that when we're thinking about asking it to predict it given a certain representation of the data, it may well be the case that the categories simply aren't very distinct. It might not really be possible to distinguish them. You know, so you might have something that's performing at 60% and it looks like, well, that stinks, but it may be actually the case that 60% is as good as it can do because the similarity between the underlying labeled sets is so strong that it doesn't have a basis to distinguish between them. So it becomes really hard to talk about in absolute terms, this is a good algorithm, this is a bad algorithm. You always have to test it for a specific task with a particular representation of data to see where it goes. This is really closely related to ideas from statistics about given two data sets with a particular mean and a particular standard deviation, how different are they, right? So if you think in statistical terms, statisticians tend to think about quantities in sets as represented by a curve. And what's called the normal distribution involves it being a bell curve, right? And so when you've got this bell curve, you've got the mean in the middle, and then the standard deviation is a number that if you add or subtract it from the mean, and you find the area under the curve between those two boundaries, in other words, you calculate a definite integral, right? That should be roughly 67% of the total area under the curve if you evaluated the integral from negative infinity to positive infinity. If you restrict it to the bounds denoted by the standard deviation, that area should be about 67% roughly. Now, where this gets interesting, right, is if you've got another bell curve sitting around. So, in other words, you've got some other set of data and you're posing a question, how similar are these data sets? How much do they in fact overlap? And so this one has its own mean and its own standard deviation, and then you can talk about how does the mean and standard deviation combination help us reason about what's the overlap in the areas under these curves. And thinking about the overlap in these areas under these curves tells us something about whether or not the data sets are actually distinct. Or I should rephrase that, the degree to which they're distinct. So when statisticians talk about things like hypothesis testing, they're basically saying if the distinction between these exceeds some threshold value, that means we're just going to declare them different. And if it's under that, we're going to declare them the same or not distinguishable. You know, a problem with hypothesis testing is the fact that that cutoff tends to be completely arbitrary. And so it's not necessarily meaningful semantically when you're comparing data sets. when we're talking about machine learning algorithms, then it's like we're addressing a lot of the same problems, but from a really different point of view. That is, we come up with data structures to represent stuff and then try to work up some mathematical way of talking about them that's amenable to being calculated by a computer program. And then we see how they do from there. So it often winds up being a really challenging issue when you're wrestling with a data set to decide, is the performance good? A lot of it then comes back around to, why do I care? So let me give you an example. I spoke last time of the fact that one of my ongoing projects here at Hendrix is a study on student retention and persistence. And so we have a set of characteristics, and then we try to build a model that predicts, which students are in danger and and therefore we should intervene with. So the question that's being posed is, which students should we intervene with? And part of then how you think about the utility of the predictor is to say, how can I adjust the algorithm so that the number of students that I've predicted I need to deal with falls within the scope of the people available to actually help them? So in other words, the output question, what am I going to do once I've made a prediction, winds up heavily influencing what we try to achieve in terms of prediction accuracy. It really comes back to that fundamental application. Obviously, more is always better, right? But to a certain degree, not all that great can be good enough. An extreme version of these scenarios is basically you come up with a data set and then you assign the labels at random. No matter how good your machine learning algorithm is, you really shouldn't expect much more than 50% accuracy because there's no there. And in real world data sets, how much distinction is there present in the data is something you often don't even know until you've tried to explore it with a machine learning algorithm. So that's some greater context and philosophical thoughts. I'm going to go ahead and move on to reviewing the naive Bayesian classifier a bit in a moment. Before I do that, I want to ask you any questions, discussion about what I was just mentioning. Yeah, Dan.
Okay, you wrote through the standard deviation and the means and talked about the overlap of the data sets.
Yeah.
What do we really care if the data sets overlap? Because, like, for example, Internet Movie Database versus Rotten Tomatoes or something like that. The data sets are likely to overlap. And it sounded like later on you were talking about whether or not we could get predictable results and whether or not there was actually intelligible stuff in there, but I'm not sure.
Oh,
I lost the bridge.
Got it. Okay, makes sense. What I was really getting at, looking at two things, is actually thinking about the performance of some different algorithms, right? And the ability of those algorithms to segregate into negative and positive. And the fact that doing that segregation depends on how much actual diversity is present within the data set.
Okay.
At the same time, I think it would be fun and interesting to compare the performance of an algorithm on different kinds of movie review databases. What that then does is it tells you something about thinking again about, say negative versus positive. How readily distinguishable are these things based on the evidence within that data set? And there's really no way to know that without doing an exploration of the data set. It's another way of saying that nothing about any of this stuff is magic, right? The term machine learning has got a lot of hype associated with it and a bit of, for lack of a better phrase, mystical woo, right? I've got a machine learning algorithm. I've got a convolutional neural network. I'm going to pick it up, feed it in, and it's just going to magically tell me everything. There's no magic. What it's doing is finding some kind of mathematically based way to talk about whether our categories actually have distinguishing characteristics to separate them. And there's nothing about the simple fact of being a data set that means there's anything to distinguish them. All of that said, once we've got multiple machine learning algorithms looking at a task, if one is outperforming the other, that says something about how the one that's doing the outperforming is finding more of the distinctions. So whenever you're faced with some kind of data problem, it turns out to be extraordinarily valuable to bring in more than one algorithm. Without that, it's kind of hard to say whether what you're doing is any good. Does that make more sense of it too? It was a great question. Other questions, thoughts about kind of this big picture thing before we begin a review of the naive Bayesian classifier? Okay, let's review the naive Bayesian classifier. So there's a lot about this algorithm that's really very confusing, and a lot of the confusion comes from a lot of the vocabulary going on. At the same time, some of the confusion comes from the fact that there are certain variations in the math that won't actually change the outcome very much. And there are other variations in the math that can utterly and completely destroy it. And it's not always clear which variations have which impacts or outcomes. Further, it tends to be the case that when an algorithm like this is confusing, giving yourself the opportunity to struggle with it and hear another explanation of it can really shed some light on the underlying issues because you know what your questions are and what to look for. So I'm going to give review, and overview. Yeah, something like that. I'm going to review the overview, give the broad outline of it, talk about the various pieces of it. And as I do this, I want you to interrupt me when I get to the part where you're like, what? So, without further ado, here we go. Thinking in bottom-up terms, with the naive Bayes classifier, the first thing we have to think about is the training process. And the reason I say that is that understanding how the classifier works and how it can be programmed, I personally find is easier to think in terms of what precisely am I asking the computer to do? What kind of data structure do I actually need to represent this thing? What is it that I'm counting? From there, we'll start putting the pieces together and see how it all fits. So, first thing that really matters for this is I'm thinking about one training sample at a time coming in to the naive Bayesian training. And as each data sample comes in, that data sample, that sentence, is going to have some words, and it's going to have a label. And because that sample has a given label, every single word within that sample is interpreted as saying something about the likelihood of that label being appropriate given something else we haven't previously seen. So what we can do then to represent this is to imagine that we've got a collection of histograms. So for each label, like you might have positive or negative, but really this scales to multiple labels. You have a histogram. And I've provided for you all a histogram class. One thing I encountered in office hours since Tuesday's class was one student who was trying to completely implement a histogram from scratch. While interesting, it wasn't really the main focus of the work. I actually provided you a histogram class so you wouldn't have to stress about that. So the way my histogram class is implemented is it's just a hash table where the keys are the things you're counting and the values are integers. And then just to make things simple, if you try to do a get on it with a word that's not present, it just returns 0 for you. In other words, if the word isn't explicitly present in the histogram, the count's just 0. And so that provides a really straightforward way of doing all of these calculations without having to special case things all over the place. Something one wants to avoid in any situation like this is where the student has sort of gone awry, is to do an efficient representation of the data structure. So this particular student had an array list of tuples of words and counts, which means that every time you look up the count for a word, you're doing a linear search. Use a hash table, it's constant time. Array lists are like attempting first data structure off the shelf to use for lots of purposes. Just remember, they're not the best for everything, and hash tables are just amazing. Use them liberally. So you've got a histogram, and what this does is it contains, words and their counts. And you do the same thing down here. And so as you get each sentence, all you really need to do is add for each word that appears to its count in the histogram. And that gives you a data structure that then represents the things you need to do the calculations that are upcoming. There are, however, a couple of other items that you're going to need to track. First is the number of documents for a given label. In my own implementation, I just used a histogram again, but this one is just saying for each label, this is the number of times I've seen it come up. And the final thing you're going to need, and I didn't talk about this Tuesday because I botched the explanation, and I'm going to fix that today, is you actually will also want to keep track of the number of distinct words that appear. The number of distinct words that appear. And this is going to help us in calculating the denominator of our individual probabilities later on. So that's how you record data for this. And this recording of data is the training process. An interesting bit of confusion that arose in multiple office hours visitors was people trying to do classification work during the training process and vice versa. So what I want to clarify is that when you're training, this is the data you're actually tracking. How often does this stuff appear? In how many documents do we have certain labels? And what is the total space of words that we encounter overall? Yes?
When you're saying documents, do you mean sentences?
I do.
Okay.
Yeah, sorry about that. Yeah, I called it a sentence, but yeah, documents basically. All right. Cool. Other questions thus far? Yeah, Innocent.
If you want to count the number of documents or sentences by using the implementation you gave us, the incoming sentence parameter doesn't have that information.
The sentence is basically an array of words, and you can loop over the sentence to see each word in it.
Sentence is an array of words.
Strings.
Okay. Oh, I see. So number of those documents, the size of that number of words that comes in a sentence?
Let me backtrack through these.
So, yeah.
This first data structure is saying for a given label, for each word that ever appeared in a sentence with that label, how many times did we see that word? This is saying for each label, how many sentences were labeled that way. This is saying, what is every word I ever saw? But don't tell me more than once. So for this, I used a set. Cool. Other questions thus far? Yes, Dan.
So overall for the algorithm, it's really just like if the word hate is associated with negative.
Is the word what? Sorry?
Like hate was
Yeah.
associated with negative. It wouldn't matter if it was hate 4 times in it, or if it's just got hate once. You essentially, it would just be a sentence that had the word hate in it. And so we get that label once.
No. That would be 4 counts
Okay.
for hate, right? Every time you see the word with that label in any sentence, that label's histogram is getting bumped.
Okay, and that's the histogram when we're learning. But like
Yeah.
in the document later on, when we're trying to classify things, are we still wanting? Oh, true, because we're still wanting to compare counts of them, right?
Yeah.
So,
So that's, yeah. So right, so if, and so this leads to some interesting stuff, right? Like if the word hate happens as often in a positive as a negative document, it'll all be there in the histogram, but it's not going to help distinguish things because when we get to that word, it just gets multiplied by the same value. And it just doesn't get us anywhere. Cool. Other questions on this so far? Yes.
So this is only applied on the training data, right? Not on the data to be classified.
Right, and let me try to clarify that further. When we're thinking about the data structure that represents the information we use to make a prediction in any machine learning algorithm, in general, we're only changing the data structure in the training process. When we're classifying, we're not changing the data structure. So supervised learning algorithms, generally speaking, don't learn on the fly, right? You give it a body of training data, it learns. And then once it's deployed, it's not continuing to learn. It's like it studied really, really hard and now it's done studying, it's just applying. There's nothing further to learn. It's a veritable masterpiece. That's not true, of course, but it's a way of saying what the mindset is. You know, you've learned what you're going to learn. Not every machine learning algorithm is like this. In particular, reinforcement learning algorithms are algorithms where self-modification tends to happen over time, even after it's deployed. The reason that works for reinforcement learning, we'll talk more about it in a few weeks, is that when you're doing reinforcement learning, how it gets updated depends on what kinds of rewards it's receiving. So a system that's got a reinforcement learning algorithm deployed is constantly determining how much reward it gets for each action it takes. And so over time, as it's actually out in an environment and exploring, it's able to refine how it makes predictions of what rewards will I ultimately get. And so in that context, you're actually kind of learning on the go and continuing to update. As you might imagine, reinforcement learning it's a lot of fun because it's reflecting more our intuitive ideas about what it means to be in the world and learning. In the world and learning. And that's exemplified by that approach. Yes?
Is it very common when you're doing this? I mean, you're reading to the data and you've got, say, like half of it for training and half of it for categorizing. I mean, to then just like reverse it and see if your results change, or just take every other one, you know, change the order in which you do it, and you would hope your results don't change significantly, but if they do, then that's indicative that it's not really working very well, or?
That's really common. In fact, it's even more common to partition, to say 10 groups, train on 9 at a time and use the 10th as a comparison group, and then actually rotate through all 10 possibilities and see what it does. And that's called cross-validation. So we could certainly do that in an assignment like this, but I didn't because I'm just trying to keep the assignment as simple as I can. But yes, in practice, that is highly worthwhile to do. I mean, often in practice, what will happen is somebody will then pick which of the 10 actually gave the best results and then just deploy that in practice. Yeah, it's fun. Because, right, obviously there's a bias in what it's going to learn based on how you selected what are the actual training items. That's absolutely the case. Yeah. Cool. Anything else up to here before we start throwing this together for the classification process? Okay. Let's think about classification. To think about classification, we'll kind of go back over the whole idea of Bayes' rule and thinking about how the data that we've collected enables us to perform calculations with the Bayes' rule. So the Bayes' rule is basically saying the probability of being in some category given some item of input data is equal to the probability of that input data appearing given being in the category multiplied by the probability of being in that category, and that's divided by the probability of having available that particular item of data. So this denominator value we can throw away for a couple of reasons. One is when we're doing a prediction, regardless of which category we're considering, we always have exactly the same data item. So performing this division is not going to distinguish the results in any way relative to each other. So how do we deal with that? We ignore it. I mean, in practice, it's basically 1.0 anyway. You know you've got what you've got. So what we're focused on is performing calculations of these two values up here. Probability of the data given the category and the probability of the category itself. So thinking back to data that we're collecting, this item right here, the documents per label, can give us the probability of the category. So this is a way of measuring in our training data set, how often does a given category actually appear on a practical level? So this is pretty easy to calculate if you've recorded exactly this data. If you know how many of your training samples had that label, and you can kind of very easily with a histogram, you just divide that by the total number of training items. This is another case where you can actually kind of throw the denominator away. Yeah, Mitchell.
So is total number of training items the total number of words that we've seen, or the total number of documents or sentences?
Documents or sentences. So what we're looking for here is how often did the label appear? Label assignment is done at the granularity of a sentence or a document.
So the total training items, which is the sum of all the different classes.
Yeah, that's exactly right. Because it's the sum of all the different class counts, that denominator is the same regardless of the class. And so it doesn't really matter if you divide it by all of those or not, because it's just the same number every time. But you absolutely need to know how many of them you got. Yes.
You can know that by adding all counts for all words from the original data set in both negative and positive. Is that
We're not operating at the granularity of a word. Words don't get labels, right? I mean, we could imagine some kind of data analysis problem where you just get a big long list of words and some words are positive and some words are negative. But that's not what we're getting. We're getting sequences of words, and that entire sequence gets a label as being positive or negative. So we're trying to find out how often does the category appear. And knowing how often the category appears depends on what level of the input we've actually stamped a label upon. Yes?
And once again, this is just for our training set data, so what have we done for the training? So if we're doing half of it, we're only wanting to count the things that are in the training set, and then that's not used again when we get to.
That's exactly right, yeah. Yes?
so in the project, when I see on the file itself, it gives me a sentence and a value about it, which might be 0, 1.
Right.
There, I can see maybe depending on the value at the end of the sentence, that means the category is positive or negative.
That's right.
But in the code that we implemented, we are given a label and a sentence.
Right.
But that sentence is only one part of the whole record, of the whole file. Is that right?
It's one part of the file, yes.
So how do we get all the file at the same time through the code?
That's a good question. And the answer is, as is so often the case when we're trying to think about how do I handle a whole lot of stuff? We write a loop, right? So we have a loop that traverses all of the sentences from the input one at a time. In that loop, we get a sentence. It has a label. We look at the label, we tell our histogram, we had one more positive. We go to the next run of the loop, it's positive, we have 2 positives. We go to the next run of the loop, there's another positive sentence coming in, or a negative sentence coming in, now we're at 2 positives, 1 negative. It's just all about incrementally updating this data as we traverse the entire training set using a loop. Does that make more sense of it in a sense?
That means this function train get called more than once. Is that true?
Yes.
Oh, and each time it's called, one line was read. Called, one line was read.
Yes.
Ah, that makes sense.
I was like,
There's no way I'm getting all five.
So that was an excellent point you brought up, Innocent, and I'm really glad that you brought it up, and I want to emphasize this to everyone. The way that this interface is designed, the train method is only using one specific item of training data, and it's getting called repeatedly in a loop that's traversing the outside file. Now, it's an interesting question. Why do it this way? And the answer is, it enables us to be flexible in terms of decoupling the process of get samples out of file and the process of update data structures accordingly. So again, it's an example of division of responsibilities in the construction of software. No matter what algorithm we're using for our learning, we know that we've got some input file where we're visiting every data item one at a time, right? That's something that both of these algorithms have in common, is that we're just doing that. So we don't have just one common body of code that actually does that walkthrough, and we have another body of code that actually does the training. So to really make this concrete, I'll open up IntelliJ, if it'll cooperate with me. We all know how that goes sometimes. Yeah, it did the little whirly thing. Yeah, there we go. All right, cool. All right, keep it coming. Funny, right? I know exactly what a computer is, how it works, and I'm still like cheering it on as if it will have some causal impact. The human mind is driven to personalize everything it encounters. Almost there. Loading project. You might wonder why this is so slow. Part of it is it's building a huge index of the code base. All right. So if I go over to Bayes Tester, the way that it works is it gets a list of file names. A data reader is an object that goes through and actually turns those files into the internal data structures that we're using. And then we have a function that takes a training set and a test set and actually conducts a test. And that's in this simple tester. So here's how it conducts a test. It calls learner.train on a text learner of labeled words. So let's look over our text learner interface. So forgive the confusion of the overloaded function name. So in this interface, it's got this default public void train method that takes a label word object as its parameter. This isn't what you're overriding, but you could if you wanted. You know, if you wanted to traverse differently the input data, you could override this and do it in a different way. This happens, for example, with neural networks, as we'll explore next Thursday. So with neural networks, you have to do some different things with the training. but not with these. This is the method you're overriding. Void train a single sentence and a label. Here's how they're put together. When you tell it to train an entire training set, this is the loop I was talking about. There's a for loop that just says loop over the training set and then call train on the sentence for I and the label for I. And that's where things sort of merge together. Yes.
Okay, looking over this, I was confused by the naming. And I'm curious how this works, because I was wondering just for a minute, it's like, is this recursion? But it's not recursion, and it knows the difference because of the parameter calls, and it's able to distinguish because of that?
Bingo.
Okay.
Yeah, so this is called function overloading. That is, you've got more than one function with the same name, and then they're distinguished based on their formal parameter lists. Looking at it now and listening to the confusion it caused, I would probably rename this to be train once. That's a nice unambiguous clarification. This is arguably a case where name overloading subtracts from clarity rather than adds to it. So you'll have to forgive my particular software development sin for now at this point. But hopefully that makes clear kind of the structure, how these pieces fit together. What you're doing is writing these. These then get used by these, the train and the test. So what does the test do? It builds up a histogram of how often you write. So for every item in the test set, it calls classify on that sample and checks to see, is it equal to the label that's coming out? And, oh, good grief. I think that's actually a bug. How embarrassing. Yes, double equals versus dot equals is so freakishly easy to mix up in Java that even after decades of experience programming it, I had that bug in code I distributed to students. Oh my. Just for your information, I'll be uploading a revised version of the code skeleton probably tonight. I unfortunately have a meeting after this class. Even more unfortunately, it's going to be an unpleasant meeting. I would much rather, details are not important. Just every now and then, you know, you're in a professional environment and you have meetings you must attend that you're not especially looking forward to. You know, it happens. You know, because, you know, people are upset about something and you just sort of have to say, well, no, we made this decision and these are the good reasons why, you know, that kind of thing. Yeah. Don't make much of it. It's just a way of saying I may not have time to upload the fix before I leave today. So I'm going to strive to get this in place as soon as possible. Get it packaged up. Yeah.
Is the fix just going to be the dot equals, or are you going to add anything else?
It will definitely be the dot equals. And something else I'm planning to add was when I was working with a student in office hours today, the student was thinking, to really understand what's going on, I want to be able to visualize a histogram. So the student had been system out print lining histograms and getting the usual gibberish from Java. So I'm also going to patch in a two-string method for the histogram class, which I think is going to make it a lot more intelligible. Yeah. Those are the two things I'm planning to do. And I mean, I could rename this as well, but maybe that's causing more confusion than it's worth at this point. What do y'all think? Should I rename it train once or just leave it alone? Leave it alone. Yeah, I think that's probably the right decision right now. So yeah, those are the two things I'm planning to do. But yeah, certainly for now, you can just patch that in. I'm now deeply curious to see what results I get from my own reference solution. Yeah, fascinating. Okay, well, if it's there, it's better that it be discovered. So there we are. Wow. Okay. Cool. where were we? Let's go back here. Okay. So now we're beginning to talk about the classification process. We've talked pretty thoroughly about calculating this value. Now we need to talk about calculating this value. And here's where the naivety comes in. We're going to say that this value is equal to the probability of a particular word given the category. And what we're going to do is, for all WI in our data sample, we're going to calculate this, and then we're just going to multiply everything together. Something I mentioned to a couple of you who are a little confused in working on your solutions. In my solution, I actually just initialized my counter variable to be this value right here because I knew I was going to multiply by it eventually. And because multiplication is commutative, you can just do it at the beginning rather than the end. But it doesn't really matter very much to talk about that. So now we have to think about these guys. How do we calculate P of WI for a given category? And I was somewhere between ambiguous and outright incorrect in how I described this on Tuesday. And so I'm going to set the record straight here so that you guys are in the best possible shape to understand what it is that we're doing. So to calculate this, what we're going to do is take the count of W of I in our category, and we're going to divide it by the sum for every word. Now, when I say the sum for every word, ultimately, this only involves words that actually appeared in our category. In principle, and this is a perfectly acceptable implementation, we could actually loop over the set of vocabulary we put together. So we could say, for every element of our vocabulary, we're going to do this. We don't really have to do that because if a word is in the vocabulary but has no representation in the category, when we ask the category, how often does that word appear, we're just going to get a 0. And so it's perfectly fine to make this loop in terms of all words that ever appeared in the category. We don't lose any information. The part that I kind of flubbed last time was in the observation that, if this is ever 0, because we're doing this multiplicative product, we nuke the entire calculation. And so we compensate for that by adding a 1 up here. But then we also compensate for it downstairs. And the way we compensate for it downstairs is we imagine adding a 1 to this value every time we've added to the sum. So a way of simplifying this is to say that this is equivalent to saying, count WI category plus 1 over the sum for all of our words of count word in that category plus the size of that vocabulary. Oh, I meant for that to be a bar. Why a bar? You've custom seen 2 bars representing absolute value, but they kind of have a deeper mathematical meaning, which is just to say magnitude or size, okay? And really an absolute value is exactly that. It's the magnitude of the value's distance from 0 on the one-dimensional number line, okay? So we're adding this. We're not adding, as I hinted at last time, the number of words in our data sentence. We're actually adding the total number of words in the vocabulary. Yes?
Is the vocabulary every word that we see in any category?
Yep. So coming up here, the number of distinct words, we can call our vocabulary, like so. And so, yeah, certainly in my implementation, the way I had done it was just maintain that set of all those words and then just ask for the size of the set. Using a set is really great for this stuff because a set as a data structure ignores all duplicates. Use a hash set, it's basically just a hash table where there are no values. It's like a hash table of only keys. And so in effect, every time you add to the set, it just sees, is this key present by doing the hashing? And if it is, it does nothing. And if it's not present, then it adds it as a key, but there just aren't any actual concrete values. So that gets us this extremely, extremely important calculation, which is at the heart of the algorithm. Yes?
So the numerator for this is the amount of times that a word appeared in the text sentence?
No, it's the number of times the word appeared in the category from the training documents. Oh, no. I am so wrong. It's exactly what you said, Mitchell. What I just said makes no sense. The denominator is the total count of the word's appearances in that category. The numerator is the total count in the category of the specific word from our sentence. So coming back over here, we want to calculate this probability, the probability of that word appearing given that category for every word in the sentence. Like so. So now coming down here, what we're saying is we have to calculate it using this formula for every word in the sentence. How many counts does it have in our category? So we're just asking the histogram for that category, how many word counts do you have? So if we look back, whoa, flew too fast. If we look back at this data structure up here, we've got a hash table mapping our category to a histogram of counts for it. We just ask this data structure, first, using your label, you grab the appropriate histogram. Next, you ask the histogram, how many counts do you have? Yes, Jake.
So our categories are just
Yes. Now, note that the algorithm can still work if you have more than two categories. For instance, what Eric's talking about with, is it a journal article? Is it a blog post? What were the other things there?
New York Times article, abstract in a medical journal.
Yeah. So you can actually do this for like 5 categories. And then you can assess individually what's its performance like for each of those data samples, for each of those categories. You know, it often turns out with something like this that the categories are not uniformly easy to distinguish. So it might do great on 3 of them and terrible at 2. When we get to handwriting next week, you know, when you build your data set, if you have both the letters O and Q in your data set, capital letters, I wish you well. Right? Those are not automatically easy for a machine learning algorithm to distinguish because they just aren't that different from each other. You know, the Q has a little tail and then there's an O. I'm not saying it won't work or whatever, but just saying, you know, that's an example where it gets hard and you're going to have some ambiguities that arise. Commercial grade handwriting recognizers will then include predictive models in terms of how frequently is a letter preceded by some other letter. And then that can be used to, in an informed way, disambiguate closely related things. So, cool. All right. So, yeah, yes.
So when you calculate the count, WI category numerator,
Yeah.
you are using statistics from the sentence you're trying to classify.
The word from the where you're trying to classify is using the statistics from the training set.
And how about the numerator?
The denominator has no influence from the word you're analyzing. So the denominator is always the same whenever you're working in a given category. Yeah. So if we examine this, we see there are no dependencies on WI down here.
WI is a category.
WI is the individual word from the current sentence we're examining. Yes.
Whereas W is just of all the words in the vocabulary, that's the number ones that were in that category.
Bingo.
Counted.
Right. So this is actually an interesting observation. In principle, you can calculate this once and store it in a variable at the very start of the method. I mean, for that matter, you can even calculate and store this when you're done with the training process and even have it as an instance variable. Because this doesn't change once we've completed the training process. So I guess I was wrong, you know. There really is stuff that looks like you're doing in the classification that can be in the training. I've always done it in the classification because mentally that's how I segregate the effort, but you can in effect pre-compute it because there's nothing here that depends on what you're submitting. The only thing that depends on what you're submitting for classification is this item right here. That's it. Cool. So once you've got these PW sub i's, you can now actually calculate this complete value. We've talked about getting this, we've talked about getting that, we multiply everything together, and now it's just may the best category win. So we examine each of our categories, we do this multiplication out for each category, whichever category gives us the highest value, and as some of you found experimentally, the highest value is sometimes something like 2.5 e to the negative 17. But it's enough. It's enough. And then we've got our classification. This algorithm is a weird mix of not terribly hard to implement, but fairly hard to get what exactly it's doing. So please don't hesitate. If you got any questions at all about what we just went over, ask away. Yes, Mitchell.
So when I know we talked about it earlier, when we were testing it, if we're just using the basic test that you gave us with the 500, what would be like a good number to shoot? Know if we got it working.
Be in the 70s with the data set I provided you. You know, that's what my solution produced. Of course, now that I had a bug in the tester, I'm making no promises. Yes.
Okay, and so classifies to actually return a string, which will be the label.
That's
and
right.
That sort of label have highest score.
That's right.
What we want to return.
Yeah. Other questions? Yes, Innocent.
Just out of, does this thing have anything to do with the lab we did in 150 code text analysis?
It's the same problem. This is a different algorithm. Yeah, so lab 10 and 150, the sentiment analysis, is approaching the same problem. Yeah. Good. Other questions? Yeah, Mitchell.
So is there no use for the like making an histogram out of your test students? There's no point in doing that?
That's correct. Yeah, that doesn't buy you anything here. The bag of words representation is fundamentally about how you build the histograms for the training purpose. Cool. Any other questions? Any other questions? Got one? Yeah.
Just a general question. I mean, we're doing this, say, for example, with words, but I assume you can use this to analyze other sorts of data. It's just a bag of values approach, essentially. And you assume all the values are independent. And, you know, it's like if you were trying to determine, we did a lab in one of our things where you were trying to predict whether or not someone would have heart issues, and they had a bunch of medical statistics. You can do a similar sort of thing with all the medical statistics and try to predict whether or not they would have such and such medical condition occur.
Absolutely. Absolutely, you can do that. You can, and this applies for most machine learning algorithms. they'll have a way of saying, this is the kind of input I'm looking for. And then part of the engineering task is to figure out, how do I adapt the data that's actually coming in and whatever representation it has so that it's actually something that the algorithm can accept. But once you've done that process, you can use anything to classify anything. So, so the heart disease example is, an interesting one. And you could imagine doing counts in terms of how often does this particular variable have a particular value. With images, you can do similar sorts of things. Bless you. You think about, I blocked the sneeze. You can think about, for this XY coordinate, every time, imagine a binarized image. So every time this XY coordinate is a high, a 1, then that gets histogrammed. Every time it's a 0, it gets histogrammed for the appropriate label. And so it kind of lets it tease out things like, if I've got a black pixel at 2,3, and that happens, 90% of the time that happens, it's with a positive, and 10% of the time it's with a negative, then that feature turns into a predictor relative to that image. Now you can see right there, of course, the naivety of the algorithm leading to a fascinating conundrum, which is, we all know in an image, the pixels are not independent, right? Phrased differently, you could permute the order in which you examine the pixels, and the algorithm should give exactly the same result. In doing that permutation, you then identify this is all the information that this algorithm is picking up and throwing in the trash. And that too is part of the art of machine learning, is identifying what aspects of this problem are being completely disregarded by the algorithm, and what adaptations could I potentially make to compensate for that. It's not necessarily easy to do, but it's important to recognize, here's where I'm running into the limitation of what it can even represent, and therefore limit its ability to make distinctions among the stuff coming in.
Okay, so for example, you couldn't really use this to draw conclusions about the impact any given piece of data had, because they're all commutative essentially.
Right.
And so, well, okay.
Right, so to some extent, this stuff is pretty hacky, which is a term we'll use again and again with every machine learning algorithm we look at. Because there's a trade-off between what do I need to do to express the underlying information, and what impact does that have on actually making the process of training it tractable. It's a really hard problem. In terms of this sentiment analysis, it comes back to the idea of, what if I permute the words in the order in the sentence? This can make no distinction whatsoever. And in English especially, the order in which the words appear in the sentence actually has semantic meaning. It's very easy to permute the order and suddenly have the sentence mean the complete opposite. And this algorithm has no possible way to account for that. It just can't do it. So then there are other things you can do, right? And this could apply to k-nearest neighbors as well. You could make as a feature whether particular phrases appear, not just words. You could actually operate on the phrase level. There's nothing intrinsically stopping you from that. It's just that at that point, man, your histogram's getting big. Right? So, instead of going on a word by word level, you could actually build your histogram on, say, 3-word sequences. I've definitely seen versions of this stuff where they do both things. They do counts of individual words and of phrases with certain radii. And then they see, okay, well, what impact does this have on the prediction? Because at that point, you're finding a way to capture kind of the deeper structure that's not expressed by an individualized word. Make no mistake, if one of you just sort of feels like trying that on this assignment, have at it. You know, kind of the spirit of the course that I'm looking for is a spirit of experimentation. I'm giving you a baseline thing I want you to try, but if you want to tweak it, try some different stuff, go for it. You know, if you just sort of feel like this aspect of what we're doing is really, really lame, and I've got an idea to make it less lame, do it. You know, I want you to try it, and I want you to see where your imagination takes you and think about how does what I imagined relate to the actual results I get. It's fun to do. All right. It's 4 o'clock. So that's what we got for today. On Tuesday, we've had several drops from the class. And so at this point, it's manageable for everybody to give an individual presentation. So that's what we're going to be doing from now on. Our individual presentations on the final day. So we'll do that. And I'll talk a bit more about some big picture issues with this kind of work. See you then.